empirical formulas. We said yesterday that there were two major parts to stoichiometry, our second unit. The first part was formula stoichiometry. That's what we're looking at here. And the second part is reaction stoichiometry, which is really much more important than this one, but this is a classic introduction to stoichiometry. When you write a chemical formula, C6H12O6 would be a formula for glucose, or a simple sugar. Notice if you look at those subscripts, 6, 12, and 6, you could reduce that formula, couldn't you? It'd be like taking 3/6 and reducing it to 1/2. It's really the same ratio, just written with smaller numbers. If you take 6, 12, and 6, what could you divide them all by? The largest number, 6, and if you did, you'd have C, H2, and O. That is referred to as the empirical formula of glucose. You can also think of it as the simplest formula, or the reduced formula if you prefer. Keep in mind, it is not the molecular formula of glucose, right? What's different between the two? The molecular formula accurately tells you how many atoms of each element are in the compound, are in the molecule. What information does an empirical formula tell you? If it doesn't tell you the actual number of atoms, it tells you the ratio. And that's going to be critical to what we do today. It's the ratio. For every one carbon, there are 2 hydrogens and 1 oxygen. That ratio is true. Okay? But let's play a game. Ready? I am thinking of a reduced fraction, 1/2. What was the original fraction?
3/6.
Nope, not 3/6.
4/8.
Nope, not 4/8. It's a fun game, isn't it?
Fourths.
Not 2/4. Nope.
Water.
Water. What the hell? Water.
150 to 700.
Okay. I can't believe nobody got it. The answer I was thinking of was 362 out of 700 out of 724. That's what I was thinking of. I can't believe you didn't get that. Okay. What's the point of that? The point is, if you know a molecular formula, it's very easy to reduce it to get its empirical formula. If you know an empirical formula, it's impossible to turn it into its molecular formula without knowing more information, right? There was no way to guess that when I said 1/2 is my reduced fraction, that this is what I was thinking of, unless I gave you some other clue, right? Because there's an infinite number of fractions that reduce to 1/2. Theoretically, thered be an infinite number of possible compounds that have that same empirical formula. C2H4O2, C3H6O3, right? There's an infinite number of possible formulas that have the same empirical formula. Going backwards to a molecular formula needs more information, and we'll do that in a few minutes as well. Try one on your own here, okay? So I'm going to give you a molecular formula or two, see if you can write the empirical formula for them. Oxalic acid, H2C2O4. Write down its empirical formula. And how about potassium nitrate, KNO3? What is its empirical formula? Victor, what's the empirical formula for oxalic acid? Are we good with that? That's correct. Okay. Emily, what's the empirical formula of potassium nitrate, KNO3? That's right, because it's already reduced, right? It's like saying, what's the reduced form of 1/2? It's 1/2. Okay? So notice sometimes an empirical formula is the same as a molecular formula, right? Okay. We are going to find empirical formulas using two techniques. Today we're going to look at how to do it using percent compositions, and then tomorrow, or maybe on Friday actually, we'll see, we'll use a harder technique called combustion analysis, a harder kind of problem. Okay? Now what we're going to do here is finding an empirical formula with percent composition. Okay, if you are given a formula, it's very easy to find its percent composition. We did that on the Ritalin worksheet, right? We showed the percentage of oxygen in Ritalin. It would have been easy to also find the percentage of carbon, the hydrogen, the nitrogen. What we're going to do here is work backwards. If I give you a percent composition, can you find the empirical formula of the compound? So, for example, a compound is made of just potassium, sulfur, and oxygen. When you see that, immediately, two or maybe three possible compounds should jump into your head. The fact that it starts with potassium or has potassium in it means it's got to be an ionic compound, doesn't it? Because potassium's a metal. And the sulfur and oxygen are probably going to be some kind of complex ion. So right away, you're probably thinking potassium sulfate, potassium sulfite, potassium thiosulfate. There's several sulfur oxygen anions, right? I'm going to tell you the percent composition. It's got 41.09% potassium, 33.69% sulfur, and what the hell, the remainder is oxygen. I did that deliberately. I could have just told you the percentage of oxygen. By saying the remainder is oxygen, then what are you going to do?
Minus all those numbers.
100% take away those numbers will give you the oxygen's percent composition, right? Be sure you have a calculator with you right now, right? We're going to be doing this together, so if you're watching this video, pause the video at different points and do the calculations yourself. If you're sitting here in class, be sure you've got a calculator in front of you. The first part of your answer. The first thing I want to see in your answer for this is a statement like this. In 100 grams of the compound. In 100, now I could have chosen any mass I wanted, 2.375 grams of compound. But 100 grams is very convenient because we were given percent composition, right? If you have 100 grams of this compound and it was 41.09% potassium, then mentally, what does that mean? We have 41.09 grams of potassium in that sample. Does that make sense? Leave some space because we're going to do unit multipliers. Underneath that, we must have 33.69 grams of sulfur. And since it has to add up to 100 grams, we can subtract and see that there was 25.22 or 25.21, I guess, grams of oxygen. 0.22? I got burned this morning. The numbers I used was 0.21, and I had said 0.22, and they jumped all over me. 0.22. Okay? We were using slightly different rounded off percentages this morning. All right, let's do something which should be, like I said earlier, it's almost a reflex, but maybe not know why we're doing it yet. We're going to convert all the grams to moles. Why? Why would we do that? We're trying to find a formula, right? What is a formula? At its simplest level, it could be thought of as a ratio of atoms, right? H2O, 2 atoms hydrogen for 1 atom oxygen. But now that we're comfortable, hopefully, dealing with moles, isn't a formula also a ratio of moles? In water, there are 2 moles of hydrogen for every 1 mole of oxygen. So because a formula is a ratio of moles, let's convert these grams to moles, and then we will find ratios, right? So if you want to write in the margin of the problem, this is step 1. Step 1, we are converting grams to moles. That might be useful to put in your margin to study from later. So I'm going to get rid of grams and switch to moles of potassium, get rid of grams, switch to moles of sulfur, get rid of grams and switch to moles of oxygen. Periodic table and molar masses. Okay, 1 mole of potassium has a mass of 39.10 grams. If you're sitting here or at home, have your own periodic table out, so you're not just taking notes, you are looking at it yourself and glancing up to see if you're doing it right. Sulfur molar mass 32.06. And oxygen's molar mass 16.00. Do not round off too much. Pay attention to sig figs. For potassium, we have 1.0501, I guess, moles of potassium. That number looks, not that attractive, nothing really nice about that, but look what happens when you do sulfur. 33.69 divided by 32.06 equals. Folks, if I look out and see people just taking notes and not doing stuff on their calculators, they're going to be hitting the road very soon, okay? So you divide those numbers and you get 1.051 moles of sulfur. If I'm in the middle of a test question and I get this, I'm thinking this feels good because the ratio there is clearly 1 to 1. So in this formula, there's going to be the same number of potassiums as sulfurs, right? Now the next one doesn't give you that same feeling of, wow, this looks good. It's going to give you a number which looks different. 25.22 divided by 16 gives you 1.576 moles.
Would Tyler McIntyre, Dawn Gray Gow, and
I'm going to just start the next step, and then
please
I'll
report
let
to
you
the
know.
office that Tyler McIntyre, Dawn Gray Gow, and Alana
What you want to do in step
please
2
report to the
is
office.
calculate mole ratios. And there's a very particular way that I'd recommend you do this. You go back to look at your 3 moles here. Circle the smallest number. In this case, we have a tie, right? Potassium and sulfur are both equal. Circle the smallest one. I'll choose potassium just for the hell of it. And what I'm going to do when I do my mole ratios is I'm going to take the other moles, oxygen and sulfur, and I'm going to divide by the smallest one. So over here, I'm going to take moles of sulfur and divide by moles of potassium. I'm going to take moles of oxygen and also divide by moles of potassium, dividing by the smaller one. My calculator, that's going to be 1.051 divided by 1.051 equals 1.000 moles of sulfur for every 1 mole of potassium, which is clearly equal to 1 mole of sulfur to 1 mole of potassium. Down here, you get 1.576 over 1.051 equals 1.499, I think, moles of oxygen for every 1 mole of potassium, which is pretty damn close to 1.5 moles of oxygen for every 1 mole of potassium. Can you see the formula jumping out at you? Right? You could, at this point, if you want, write the formula as K S O 1.5. Do you agree? What's the small problem, though, with that? You never leave subscripts that aren't whole numbers. So what can I do with that? Double everything, and you get K2S2O3. And there is your empirical formula. Okay? Have a great day.